Okay, so we start the last talk of the day by Takuya Okawa from SISSA, Italy, and he's going to talk about predictive curvaton from thermal misalignment.
Thank you for introduction, and thank you all for being here today. As introduced, I'm Takuya Okawa, coming from SISSA, as well as Institute for Fundamental Physics of the Universe, which is also interested. Today, I would like to share our work on curvaton mechanism, which is one of the extensions of inflation scenario, in which it's easier to generate curvature perturbation, and how it would be like if combined with thermal effect, in particular thermal effect called thermal misalignment. If you have any questions, feel free to ask me anytime. I'm happy to answer the questions. Before going into details, probably it's nice to going over inflation briefly a little bit. Inflation is a very short period at the beginning of the universe in which the universe was approximately exponentially expanding. The idea of inflation was proposed many decades ago, but there still remains interest and motivation of studying this, mainly because it can address two major problems that are otherwise cannot be naturally explained within the standard model of cosmology without inflation. One of the problems is the horizon problems. If we think of temperature distribution of CMB sky, we observe it to be nearly isotropic, which implies all points on the last scattering surface of photons were in equilibrium at that point. But on the other hand, if we estimate the size of particle horizon, which measures how large region in the universe were in causal contact, it can extend only of order 1 degree of CMB sky observed today, meaning that isotropy of temperature is not necessarily guaranteed. Again, but we can impose this as the initial condition, but if we want to avoid placing and using very convenient initial condition, inflation provides one of the natural explanation for this isotropic temperature distribution. Another problem is the flatness problem, which is a fine-tuning problem about the curvature of the universe. We observe the curvature of the universe to be close to zero. In other words, this universe is close to the flat universe. This is, in some sense, a problem or concerning, because curvature, precisely speaking, density parameter corresponding to the curvature, is increasing function of the physical time, both in radiation-dominated era and matter-dominated era, meaning that in order to have small curvature at present, this universe has to have tiny 10 to the minus many tens of curvature when it was born. Again, we can impose this as the initial condition, but if you want to avoid using convenient assumption, inflation provides natural explanation for small curvature. Plus, in many extensions of standard model of physics, we tend to produce many unwanted relics, topological defects. Famous one is magnetic monopoles from grand unified theory. If inflation exists, and monopoles were produced before or at least during inflation, number density of monopoles are exponentially diluted away because of the exponential expanding of the universe. Moreover, it can account for density fluctuation of the universe that ends up being large-scale structure of the universe, again, which we have observed. Because light field during inflation can acquire fluctuation of order of Hubble scale during inflation that serves as seeds, which grows mainly in matter-dominated era, undergoing nonlinear dynamics, including gravitational collapse, forming galaxies, galaxy groups, or even larger structure in the universe. And it is consistent with what we have observed so far. So inflation is successful in explaining variety of stuff, but on the other hand, there is a downside. One of the downsides would be difficulty in explaining all of observational facts while making inflation model minimum. Let's consider the minimal case where we have only one inflaton whose potential is described by only one form of the power law. In that case, inflaton, this scalar, has to be responsible both for driving inflation at the beginning of the universe and generating density fluctuation to form large-scale structures of the universe. These two are already difficult to achieve at once, as illustrated in this plot. Vertical axis shows tensor to scalar ratio, which measures how large primordial gravitation wave signal is. And we haven't observed primordial gravitational waves, placing upper bound at around 0.03 or 4. Horizontal axis is for the primordial tilt. We know the power spectrum of density fluctuation, scalar fluctuation, is nearly scale invariant, but has small red tilt, which means this ns has to be close to 1, but cannot be exactly equal to 1, has to be slightly smaller than 1. Then this minimal case, corresponding to yellow, orange, dark orange, and red blobs and lines, to be fair, we could choose a weird shape of the potential, phi to the power of 2/3, but the most natural case, mass term phi squared, is already excluded with a large significance. Then it will be natural to think about extend inflation model from the minimal case a little bit while keeping model a little as minimal as possible. One of the extensions is curvaton mechanism, which I will be talking about. In the rest part of my talk is divided into 3 parts. First, I will explain what is curvaton mechanism. Second, I talk about thermal misalignment, which turns out to be somewhat inevitable for curvaton. And at the end, we will try to accommodate thermal misalignment effect into curvaton mechanism to see if we are able to construct model more consistently at the same time more minimally. I start from curvaton mechanism. Curvaton mechanism is one of extensions of inflation scenario in which it's easier to generate curvature perturbation of the universe because we add, in the minimal case, one more scalar field which is responsible for generating curvature perturbation. Then inflaton doesn't have to take this role anymore. It has to explain exponentially expanding universe at the beginning. Let us consider the case where there is only one curvaton whose potential is mass term plus interaction term, which describes curvaton decay to the standard model particle at the end. It has to decay at the end to start standard model of cosmology before BPN. Initially, curvaton is a spectator. Correspondingly, its energy density is subdominant compared to radiation energy density or inflaton energy density at that point. After the inflation ends, reheating is completed. I'm assuming instantaneous reheating for simplicity. Energy density of radiation drops rapidly, proportional to 8 to the power of 4, scale factor to the power of 4, whereas energy density of curvaton remains constant because it doesn't start oscillating until Hubble parameter drops comparable to the curvaton mass. Once Hubble drops to the curvaton mass, curvaton field starts oscillating about its quadratic potential, decreasing its energy density proportionally to the scale factor to the power of -3rd. This decrease is milder relative to the decrease of radiation energy density. So relatively, energy density of curvaton still increases compared to energy density of radiation. At the end, when curvaton decays, curvaton might or might not dominate energy density of the universe depending on how long these frozen era and oscillating era are. When Hubble drops to the decay width of curvaton, curvaton just decay, becoming radiation. In this minimalistic scenario, we have 4 parameters. 1, Hubble during the inflation. 2nd, curvaton mass. 3rd, total decay width of the curvaton. 4th, initial displacement of curvaton field, which we have to choose very conveniently to explain the amplitude of observed power spectrum of scalar fluctuation. We observe it to be order of 10 to -9th. Correspondingly, we have to give misalignment for curvaton comparable to a few thousand times of Hubble during the inflation. Plus, there is another observational constraint coming from non-Gaussianity. In general, curvaton mechanism produce non-Gaussianity of order 1 in almost all of cases. And in particular, when this parameter small r, which describes how large fraction of energy density is accounted by curvaton sector, r close to 1 means curvaton is dominant when curvaton decays. R is 0 means curvaton is quite subdominant when curvaton decays. If curvaton is subdominant, if r is close to 0, first term in this expression blows up, making non-Gaussianity much larger compared to order 1, which is inconsistent. So we have to make curvaton dominant at the point of curvaton decay. In other words, we have to make curvaton decay late enough so that we can make curvaton to radiation energy density ratio grow enough during frozen or oscillation era. Combining all of these, first we can get model-independent constraint. Model-independent here means we are not specifying interaction term, which describes curvaton decay to the standard model field. First, I would note that this nearly diagonal black dotted line, it corresponds to decay width equal to curvaton mass. So above which decay is non-perturbative. We wouldn't call it viable, but for completeness, we are showing that regime as well. In order to make FNL small, we cannot choose Sheehan shaded region. Curvaton has to decay before BVN, otherwise we mess up big bang nucleosynthesis corresponding to orange shaded region. Curvaton has to be light enough compared to inflation scale because otherwise it cannot acquire density fluctuation. Density fluctuation is exponentially suppressed. Purple region is excluded. And as we can see, if inflation scale is very high, solid lines correspond to the highest possible inflation scale, 5 times 10 to the 13th GeV. We have a chunk of large portion of viable parameter space, but if we use low scale inflation, at the end, we entirely close perturbative regime. Dotted line corresponds to H inflation of order of 10 to the 8th GeV. But again, as long as inflation scale is high enough, we have relatively large degree of freedom for choices of parameters. Then we next wanted to be more concrete. So we chose dimension 3 couplings with Higgs to describe curvaton decay to the standard model particles. We chose this term because this is the only possibility if we want to make interaction term super renormalizable, Gauge invariant, and describing decay of curvaton without introducing any mediators. And of course, this term does describe decay of curvaton to Higgs before electroweak symmetry breaking, as well as after electroweak symmetry breaking. But after symmetry breaking, this scalar acquires mixing with Higgs. So even if this scalar is lighter than twice of Higgs mass, it can still have a decay channel, even if nearly massless, because there is a loop decay to 2 photons. This plot shows total decay width as a function of scalar mass. In particular, when scalar mass is around GeV, we have resonant decay to hadronic states, which is not easy to estimate. So we borrow the expression from the last cited paper here and connect that expression to the heavier scalar mass side and lighter scalar mass side. And what's nice about this coupling is thanks to the mixing with Higgs, this scalar is detectable all in laboratory environments, astrophysical environments, and cosmological environments. This plot shows where can be probed by one of lab astro-cosmo environments in mixing versus scalar mass parameter space. It's not below 100 MeV parameter space is almost entirely excluded unless we choose quite tiny mixing. Even we go heavier side, up to 100 GeV, we have relatively constrained parameter space. I will come back to this point later. Then at the end, we see where it's allowed for curvaton scenario. Again, we chose the most optimistic case for this plot, which is the highest possible inflation scale. Then we have still a relatively large chunk of a parameter space, usable parameter space. Again, bounds includes curvaton has to decay before BVN, curvaton has to dominant at the point of curvaton decay. They are bounds from laboratory and astrophysics cosmology. The red region at top left corner is just unrealizable. Effectively, mixing becomes larger than 1, so this is not possible. A gray region at top right corner is excluded, where we don't prefer this region because of naturalness. At loop level, Higgs and scalar acquire mass. We don't want that to be larger than their bare mass, excluding gray region. Also, this interaction term induces quartic self-interaction term by diagram with 4 external scalar legs with 1 loop consisting of 4 Higgs mediators. It turns out this self-interaction can be dominant compared to the mass term because we have to give relatively large displacement by hand at the beginning. It has to be higher than H inflation by a factor of 2000 or 3000. Above this magenta dotted line, self-interaction term becomes dominant compared to the mass term. Correspondingly, we have to be careful so that effective mass of curvaton cannot exceed inflation scale because, again, if so, perturbation, fluctuation of scalar field is exponentially suppressed. But still, we see a relatively large chunk of parameter space as long as inflation is high scale enough. So we thought it would be nice if we can make it more minimal. In particular, we are at this point giving initial displacement, misalignment for curvaton by hand. But looks like there's a possibility to give misalignment rather than by a thermal effect rather than giving by hand. If this is possible, the last parameter, sigma star, is not the parameter of the model anymore, just because of the fact that curvaton has to have interaction term with the standard model because it has to decay. This interaction term at the same time can explain large enough displacement to explain the amplitude of power spectrum of scalar fluctuation. So the rest of my talk, we are trying to pursue if there is any possibility to include, to realize this scenario. Then we would like to understand what is thermal misalignment. A thermal misalignment is the effect that a field is shifted from the origin towards somewhere else because of finite temperature potential. In particular, this effect is effective when temperature is high enough. What's nice about this misalignment mechanism is, unlike conventional classical misalignment case, behavior of the scalar field at late-time universe is not sensitive to its initial field value, as we can see in this plot. As long as misalignment given by thermal effect is large enough compared to initial misalignment, behavior at the late universe, in particular after the onset of field oscillation, coincide regardless of the initial misalignment. Then next natural question would be, where is this come from? In order to answer to this, we are interested in effective potential of the scalar, which can be divided into three level part, loop level part at zero, which we also have at zero temperature, and finite temperature potential, which is loop level at the same time only exists when temperature is non-zero. And we are interested in the last part. The last part looks like temperature to the fourth multiplied by this function JV, which is a function of Higgs mass squared by temperature squared. It depends on Higgs mass squared because we are assuming interaction with Higgs. And also there are contributions from Goldstone modes of Higgs, but phenomenologically their effects are the same to the physical Higgs. So I only consider the first term for the time being. At high temperature, if I expand this orange shaded function, at the leading order, I get a constant term, which corresponds to constant potential term. For now, it is not so interesting because after being differentiated with the field, it goes away because this term just shifts the potential overall by some factor. Then maybe interesting term is the second leading order term, which is proportional of the Higgs mass squared times temperature squared. Then what's crucial is, since we are assuming coupling linear in a scalar field, because we want to describe decay by using this interaction term as well, there is a contribution on Higgs mass linear in the scalar field, ends up producing effective potential of the form, again linear in scalar field. Then if this term is plugged into the equation of motion, it serves as if there is a source term coming from the thermal bath, shifting the scalar field from the origin towards somewhere else. Schematically, what's happening is the following. After the inflation ends, reheating is completed, there exists hot plasma and scalar fields. When temperature is much higher compared to Higgs mass, thermal potential is dominant. In particular, this term, mu sigma t squared term, shifts curvaton field away from the origin. Once output drops comparable to the effective mass of curvaton, this scalar starts oscillating. As the universe expands, temperature of the universe drops. At some point, it becomes comparable to Higgs mass. Then this thermal potential becomes moderate. This scalar starts rolling back toward the origin, and at the end, it starts oscillating about the origin under the tree-level potential when temperature of the universe becomes quite low compared to the Higgs mass. And combining all of these, we expect this kind of behavior. This plot shows field excursion as a function of physical time for a variety of initial misalignment. And we can see that as long as misalignment given by thermal effect, shown as black dashed line, is larger compared to initial misalignment, evolution of a field after the onset of oscillation are nearly the same regardless of initial misalignment. Then the last question is, can we incorporate this into curvaton mechanism? More precisely speaking, we want this misalignment to be large enough to be consistent with the observed amplitude of scalar power spectrum. But in order to make it large, we have to make coupling with Higgs large enough, which makes decay width smaller. Then curvaton might decay too early before dominating the universe, which is what we don't want. So our task is whether if there is a choice for coupling for given H inflation and scalar mass, so that we can generate large enough misalignment at the same time, make curvaton dominant at decay to avoid too large non-Gaussianity. And the answer seems to be yes, there is a small region in the parameter space, allowed parameter space that is viable around scalar mass around 1 GeV if inflation scale is order of 10 to 11th GeV. And these three black dotted, dashed dotted, and dashed line correspond to different choices of H inflation, but as we can see here, 10 to 10th and 12th GeV are already in excluded psi. So H inflation has to be quite close to 10 to 11th GeV. We also show bounds coming from Love's astrophysics, and FNL decay has to be before BBN. And also for some regime, so surprisingly, it turns out thermal misalignment is super effective. And for some regimes, in order to make AS small enough, comparable to 10 to minus 9th, we had to choose H inflation large enough, but we cannot choose H inflation too large because of the bound coming from non-observation of primordial gravitation waves. Correspondingly, red region is not allowed, not consistent. Lastly, what we found it nice is this viable region is also probable by cosmological, astrophysical, and laboratory environment. So I will briefly mention what we can do. There are a variety of measurements from cosmology, but these are all relying on the fact that this scalar can be produced from the thermal bath in the early universe. If they decay relatively early, around BVN, it could contribute to the effective degree of relativistic freedom, increasing N effective, or it can modify abundance of primordial nuclei produced during BVN, especially helium-4, corresponding to orange region. If decay is relatively late, but before recombination, energy injected from decay products of a scalar distorts CMB spectra, which is highly constraining, corresponding to green region. If decay of scalar takes place around recombination, it changes ionization fraction of electrons at relevant epoch, changing optical depth of CMB photons, which we can observe indirectly by temperature anisotropy of CMB. Correspondingly, purple region is excluded. Even if decay lifetime of scalar is too long, quite long, comparable to the age of the universe, we still could probe this scalar by looking for diffuse X-ray background, because firstly, because scalar can decay to 2 photons, secondly, because we also have photons as secondary products from E plus E minus from this scalar decay. With the same spirit, there are astrophysical bounds. By saying with the same spirit, I mean all of these bounds rely on the fact that scalar produced inside the medium of supernova and neutron star. If scalar, after produced, escape from the object, they contribute to the cooling of the object. But at the same time, they can produce gamma ray signal or 511 keV photon signal. because a dominant decay process for MeV, 100 MeV scale scalar is E plus E minus. Decay to E plus E minus is dominant, which could produce 511 keV photon line. Plus, even if decay length is not so large, it could inject energy to the expanding envelope. Then this expanding energy might be too large to explain what we observed corresponding to the red shaded region. And lastly, this Higgs boson scalar curvaton can be produced in the lab, which we can observe via their decay products or as a missing energy. Also, presence of this scalar slightly modifies property of Higgs, by which we can indirectly probe this scalar. So as a summary, inflation is indeed successful in explaining several problems, but we tend to require a highly extended model to explain everything. But that's okay. And as a one-off trial, we tried curvaton mechanism, in which generation of curvature perturbation is relatively easier because we add one more scalar field. But we tried to make curvaton mechanism more minimal compared to the conventional scenario, where initial displacement for curvaton is given by hand. We rather try to give this misalignment by using the thermal effect. And this thermal effect must exist because curvaton has to decay to the standard model. In order to do so, it's natural to assign interaction term linear in the curvaton field, which unavoidably shifts curvaton field from the origin toward somewhere else. And at the end, we found that there is a viable space in which this model becomes consistent if scalar mass is around GeV and inflation scale is around 10 to 11 GeV. What's nicer is that region could be observable by all of cosmology.